Uh, Welcome to lecture number 34 of this groundwater hydrology course. In this lecture number 34, we will cover saline water intrusion in aquifers. Topics to be covered are geochemical, investigations, control of saltwater intrusion, and practical modeling of salt water intrusion. In geochemical investigations, we can use certain parameters to identify whether the saltwater intrusion has happened in a particular aquifer or not. So, seawater has got seawater has a uniform chemistry due to the long residence time. Of the major constituents. So, main point is that predominance of chloride and sodium predominance of chloride and sodium with molar ratio of 0.86. If the aquifer is not anthropogenically polluted, the fundamental, if the aquifer is not anthropogenetically polluted, the fundamental cations uh, calcium and magnesium and to a lesser extent the alkali ions sodium and potassium the fundamental cations are mostly this calcium, magnesium, and to a lesser extent they are alkali ions sodium and potassium. So, to identify the saltwater intrusion different indices or parameters can be defined. The first one is salinity. Salinity. So, time series of steadily increasing chloride concentration can indicate the early evolution of the early evolution of a salinity breakthrough from seawater. Next parameter is chloride to Br ratio. Cl or chloride Br ratio can be used as a reliable tracer. Because both Cl and Br are usually behave conservatively. So, Cl and Br this behave conservatively, and in case of seawater this Cl to Br ratio, this weight ratio is approximately 297. For anthropogenic sources like wastewater effluent or sewage effluents, this Cl by Br ratio is up to 800. The third parameter is sodium by chloride ratios. Sodium chloride ratios of salt water intrusion are usually lower than the marine values, which is less than 0.86 molar ratio. The fourth parameter is calcium magnesium, or you can have calcium with bicarbonate and sulfate. So, these two ratios in seawater indicates with a high salt water intrusion if it has got value greater than 1. So, high calcium magnesium ratio or calcium bicarbonate plus sulfate ratio, both are greater than 1, indicates seawater intrusion. Other than this, you have oxygen and hydrogen isotopes. Stable oxygen and H isotopes can be used to describe the mixing process between seawater and fresh water. Fresh groundwater aquifer is generally depleted in both and deuterium relative to seawater. Mixing of fresh water and seawater should result in linear correlation. And the last one is boron isotopes. One of the process that modify the chemistry of seawater intrusion is the adsorption of potassium. Adsorption of potassium, boron and lithium onto clay minerals in the host aquifer. These elements are relatively depleted in saline water associated with seawater intrusion. So, elements are relatively depleted in saline water associated with seawater intrusion. Thus, this boron isotopic composition can be used for identification of salinization sources, in particular to distinguish from anthropogenic contamination such as wastewater. So, boron isotopic composition of groundwater can be used as a tool to discern the salinization sources. So, these are the parameters with which saltwater intrusion can be identified. Next thing is that in density dependent flow, the density depends on the reference density, temperature and concentration. Similarly, dynamic viscosity is also a function of density or dynamic reference dynamic viscosity, temperature and concentration. So, these two can be treated as equation of state for solving the both flow and transport equations. So, for the governing to solve this saltwater intrusion or saline water intrusion process, we need to use density dependent flow equations, and flow equation is density dependent. That means there is a relationship between this hydraulic head with density, and these equations can be solved in a coupled sense. So, the first equation is the flow equation. So, this is a normal density, rho 0 is the reference density, F is the storage coefficient, H is the hydraulic head or total head, T is time. So, this is time dependent term. Then we have this is permeability tensor or hydraulic conductivity tensor. This is this defines the axis direction, because in z direction we need to consider one extra component in case of Darcy's law. This q star this rho star is the density of injected or extracted source or sink, and q is the discharge rate of source or sink, and this is the transport equation. So, this density is related to this concentration with the relationship that defines that this density is basically rho naught plus 1 plus your epsilon or alpha divided by Cs, where this alpha is basically 1 rho s minus rho naught divided by rho naught, and this is the density of water, groundwater. This is reference density. This is density ratio or relative density difference. So, if we take usual values, then this rho naught is 1000 kg per meter cube, 1000 kg per meter cube, then rho S is 1025 kg per meter cube. Thus, this alpha or relative density difference ratio, that becomes 0 to 5, and this CS, which is usually concentration of sea water, that determines the whole thing. Now, in this transport equation, this theta is moisture content, the C is concentration, this is again the temporal or time dependent term, this is advective term, and this is diffusive term, this is also alpha prime is the modified compressibility term, theta is again moisture content, concentration, this is total head, Q is the discharge rate for source and sink, and C in is the concentration of incoming or outgoing, that means injection or extraction rate. Similarly, the Q star, this rho star is the density of the injecting or extraction related fluid. So, these are the terms which are there in the transport equation. Now, as we have seen that the density is related to the reference density, density is related to reference density with the relationship rho and rho naught with 1 plus alpha, and this is concentration divided by CS. So, we can easily see these two equations are interrelated, and it can be solved only in coupled sense. So, as because there will be saltwater intrusion in coastal aquifers, so we need to take some kind of countermeasures. So, one thing we can do is that we can manage the demand. By managing the demand itself, we can counter this is one kind of countermeasure for the saltwater intrusion management. So, then non-potable water reuse. So, non-potable water reuse is the second measure. Third one is the modified pumping rates. So, we can have modification related to pumping rates, and with the modified pumping rates only we can control the seawater intrusion. Then pumping caps, with the pumping caps also we can control the saltwater intrusion. Well relocation, let us say that we have a well which is near to seashore or near to your shoreline, then it is obvious that there will be extra pumping from those wells, and due to those pumpings there will be intrusion of seawater at a faster rate, and if we relocate it in the inward direction, then at least we can check that seawater intrusion in the coastal aquifers. Then conjunctive use. Conjunctive use is that we can use different combination of surface water, groundwater, so that people can use a percentage of groundwater from their coastal aquifers and a percentage from surface water source or nearby rivers. So, that way people will not be that much dependent on the groundwater aquifers or coastal aquifers, and we can check the saltwater intrusion. And the first one and the last one is the aquifers storage and recovery. So, aquifer storage and recovery is the most important one, because we can store water in a certain aquifers and we can extract that water in future. That way, if that is connected to the seawater phase, then it can be it can act as injection barrier. Also, if it is not hydraulically connected with the aquifers, so we can store good quality of water in the aquifers and we can reuse it in future. So, tapping alternate aquifers, let us say that there is saline water intrusion in this particular aquifer, then one can try to tap a lower aquifer which is not hydraulically connected or not that much affected due to saline water intrusion. So, that way we can control the seawater intrusion. Basically, it is by reducing the demand from this particular aquifer, and we are transferring that extraction from a different aquifer, or we are transferring that extraction thing to a different aquifer. Next is extraction barrier. Let us say that we have a sea here, then saline groundwater, this is our fresh water and this is our production well. So, and this is another barrier well which is near to your coast, and this is our initial groundwater table. So, if we start pumping, there will be a movement of this saline groundwater towards the fresh water, fresh groundwater or freshwater aquifer, and this barrier well will act as some kind of semi barrier thing, and it will reduce the seawater intrusion effect by pumping saline water from the pumping wells, and we can safely use our production well for some amount of extraction, but there should be sufficient limits or there should be caps, so that we can check the saltwater intrusion. So, this is the original interface, and now this is the final interface after the seawater intrusion. Then scavenger wells. So, these wells are deep wells, and these wells are meant so that we can arrest the total saline groundwater, and it goes up to full depth. So, this is our final groundwater table. This was our initial one. So, we can safely extract water from the production well from our freshwater aquifer. Injection barrier. With the injection barrier, in case of barrier well, we have already seen that there is extraction barrier. Now, we can use the same barrier well as injection barrier. We can inject water into these barrier wells, so that water will spread into this aquifer, and it will reduce the effect. Although this movement is shown towards sea, but this is in a scaled up view. There will be a smaller effect or smaller retreat towards the sea. Now, another point is land reclamation. With the land reclamation, as this is our groundwater table and this is our sea level, we can have a different interface position with the land reclamation. So, that may reduce some kind of seawater intrusion effect. And next one is the impermeable barrier. So, impermeable barrier is basically made by injecting bentonite slurry or highly some kind of material, so that the porosity the pores are filled with that material and the hydraulic conductivity will be reduced drastically. So, with this kind of impermeable barrier in position, there will be reduced effect and there will be slow movement towards this production well. So, by this method also we can check the saltwater intrusion towards coastal aquifers. Then another one is the surging pit. So, surging pit, this wall is basically impermeable, and these two walls are permeable walls, and water is filled in this surging pit and it is just parallel to the coast. So, with high velocity, if we pass the water, then the saline water intrusion effect can be reduced. This is the production well and there will be reduced effect. So, this is basically one kind of recharge effect and impermeable boundary effect. So, our goal is to maintain the quality and quantity. So, we need some kind of careful planning of withdrawal strategies for control and remediation. Remediation not in true sense, but we can easily control the saltwater intrusion with different type of countermeasures. So, now I will discuss one case study of Nellore district in coastal Andhra. So, coastal aquifer of Andhra Pradesh, that is in Nellore district. So, these are two mandals, Alur and Vidavalur, situated in the Nellore district, and we have taken these two mandals for saltwater intrusion modeling and control. So, objectives were collection of all head concentration pumping data for the study area along with boundary condition and parameter estimates. Next is implementation of a 3-dimensional finite element based numerical saltwater intrusion model for the coastal aquifer study area, and calibration of the developed model for the study area, and predicting the future saltwater intrusion scenarios and evaluating the management strategies for possible control of saltwater intrusion. So, this is the study area and total area is 355 kilometer square. This is the boundary between Alur and Viddavalur. So, to model this kind of coastal aquifer regions, basically these are having one coastal boundary, that is Bay of Bengal, one is Penner River boundary, another two boundaries are political boundaries, that is Alur Mandal boundary and Vidavalur Mandal boundary, and this black dots these indicates the location of pumping wells. Generally we have allocated these pumping wells in such a way that it represents the pumping scenario of each of the villages. These are the villages which are situated in these two mandals. So, in a particular village there can be more than one pumping well, but these are basically representative pumping wells for the study area. So, number of villages in Alur Mandal is 15, Vidavalur is 10. So, area wise is Alur is bigger and normal rainfall is almost same, and the major crop is paddy, but recent few years there has been shift in the cultivation aspect. So, this is the basic stratigraphy of the study area with the RL values from different sources. This model was prepared. These are the pumping wells, these are basically strainers, and it has been found that bedrock was not encountered even at drilling depths ranging from 250 to 500 meters. So, we have considered the top portion only for modeling. So, first thing is that we have considered 12 meter thick sand layer, then second one is 3 meter thick sandy clay, and the last one is sand layer with 15 meter thickness. So, assumptions that were made because of non availability of some of the data sets. Recharge rate in the form of infiltration is taken as 15% of the normal rainfall in that particular period. The river boundary is assumed as no flow, as Penner river remains dry most part of the year in this region. Although there is some amount of discharge, but we have assumed it is a no flow boundary or not contributing to the study area. Seasonal fluctuations are not considered, tidal effect is not considered. Then the pumping and recharge rates are averaged over the year. The total value is the total pumping occurring over the year, and you already know this is the equation. In case of epsilon there was alpha. So, this is a 3D view of the study area, and this is with finite element mesh, and you can see that for draft values, the maximum draft value assigned for a particular well is this much, and minimum is this much, and in case of Vidyavalur it has been found that drafts are very high. So, you have increased the draft based on the population and other data. So, calibration and validation, the calibration process is carried out for the time period between July 2000 to July 2002, and simulated and observed head and concentration values are compared with the July 2001, July 2002. The model is then validated for July 2003, 2004, mainly in the head in terms of head values, and as estimated data is very scanty for 2003 and non-existent for 2004. Longitudinal dispersivity is considered as 50 meter and lateral dispersivity 15 meters. So, calibration trials with sand layer with a particular hydraulic conductivity values, it has been found that the upper region and the lower region it is not matching, and also in upper region there is some kind of deviation, but not that much, but in the lower part it is not completely matching. It may be due to the parameter values or due to the boundary conditions. So, groundwater modeling is basically it is either you can adjust the boundary condition or depending on the actual values, or if you do not have that you can try to adjust the parameters to get the actual value. So, calibration trial 2, in that one also it has been found that there is deviation in the lower portion or Vidyavalur region, and in third trial also it is not matching. So, in case of 2001 it is almost matching with the actual one. So, it has been found that simulated and observed values are well in this 45-degree line, and simulation for 2001. So, simulation difference, so concentration scenario difference is only here in the internal portion. This is the observed one and this is the simulated one, and simulation for the 2002 also, it has been found that observed and simulated, the middle portion only there is some kind of deviation, and the simulation for 2003 also, it is found that there is some kind of deviation for that same region, and simulation for 2009 with the existing pumping pattern, this is the scenario, but it has been found that internal region we have high concentration values. This is due to the fact that there can be some kind of inland salinity for this region. So, 3 scenarios are considered for control of saltwater intrusion. So, in Vidavalu region, the 5 wells are considered near to seashore. Then it has been found that there is decrease in concentration for a reference point 1 with that scenario. Again near the Allur Mandal, if 5 wells are installed as extraction barrier wells, then for the reference point also there is increase in concentration level, but the rate is much slower as compared to the existing pattern. So, scenario 3, if 5 wells are installed within that inland salinity portion, then also there will be decrease in concentration values for that region. So, this is the comparison of concentration for 2009 scenario 1 and 3. The scenario 4 also same thing has been experienced. We can have 2 objectives for any saltwater intrusion management model, that is production well, extraction barrier well. This is the groundwater flow transport equation which relates the concentration with the flow transport relationship. There should be some kind of limit on concentration, that means the concentration in the region should not exceed some value, and the pumping, there should be cap on the pumping values, and this is basically maximizing the pumping from production well, minimizing the pumping from extraction barrier wells, and both pumping from production well and pumping from barrier wells, these are bounded variables. So, that way one can formulate the management model for saltwater intrusion, and it can be solved for any particular aquifer. So, this is the end of saltwater intrusion, saline water intrusion modeling, and basically geochemical investigation, control of saltwater intrusion, practical modeling of saltwater intrusion, and last we have discuss this management aspect of saltwater intrusion. Thank you.